thank you very much for the introduction, and thank you all for coming. It's a pleasure to be here, and I thank the organizers for the invitation. So I'm Claire. I'm from Deep. Oh, the microphone. Is it better now? It is supposed to work. Yeah. Okay. So I'm Claire. I'm from Deepmind, and I work on Bandits. I've been working on Bandits for about 4 years now. And well, today I wanted to present what I've learned on Bandits and what I've done with what I've learned during my postdoc at Amazon in Berlin with Alexandra Carpentier and many other great people. So I want to give you a little bit of motivation of the problem that I'm looking at in the first place. So we are in a sequential learning environment. So our agent, the guy that is learning here, is interacting with an environment. So at each round, at the beginning we have no data. There's no data at all. And at each round, I take an action, which is a vector in RD. And the environment sends me a feedback, which is a function of this action. So it's a parameterized function with some parameter theta that is unknown. So I don't know this function f theta of at. And the environment sends me noisy feedback. And the agent has to learn a policy that is a way to choose the next action given the information that has been observed so far. But in a real world setting, what happens? This environment with which you're interacting is something like a user. So typically you're presenting, ads or recommendations or products. Like I was working for Amazon, so we were presenting products to people. And people would put them in the basket and, go for a drink or something. And then like after a few minutes or a few hours, they would actually buy it. And I was optimizing on the clicking on buy, the button buy. So this would take a long time. So I would model that by a delay buffer. So the agent sends an action. This is a recommendation. The environment does something, like sends a feedback. And then this feedback stays stuck in a delay buffer that generates some random delay, dt here. And after a while, this feedback is sent together with the action. It's sent to the agent that is going to be able to update their policy. But the problem is that in the meantime, the agent has to make actions. So the question here is how to play with linear bandits, how to learn an efficient policy for the agent. And the second question is how to deal with delays. So we're going to see a little bit of both things. So the very light program of today is first a little bit more of background on linear bandits, and then how to deal with delays in a real-world setting. So linear bandits, what is it? At round T, like I said, so you said you select an action which is a vector in RD, and you observe a reward that we will assume to be a linear function. This is the linear contextual bandit part. So this reward is going to be a linear function of your action with some sub-Gaussian noise. So we assume the noise of the environment to be light-tailed. We don't want anything too mean to us. And the goal of the agent is to keep the regret small. So what is the regret? It's a cumulative sum of losses. And the loss in that case is the gap between the reward that you would have got if you had made the optimal action and the reward that you got. So this quantity is theoretical. I cannot measure it at each round. But I want to design a policy that, in expectation, minimizes this regret. So how are we going to do that? So first, I want to just comment quickly on this setting. So I assume that the action set at each round is some subset of RD, like some subset. What does it mean? It's like something that's very arbitrary. It's like it's selected, it's fixed in hindsight, or it's selected by some, I don't know, adversary maybe. And so a typical setting in a real application is that you have a user, represented by features, vector features UT, and you have your actions that also might have features, and you have some joint function that creates like an embedding of users and action features, and creates like outputs a contextualized action vector. This is just a function of UT and AI for each of the actions of your catalog. And this, because you make no assumption at all on these joining functions, you can actually just imagine that it's like it samples vectors on a closed convex set in RD. And that's why we make no assumption, and that's why we want an algorithm that is robust to any choice of action sets that can be either sampled from an unknown distribution or just chosen in hindsight by the environment, but you don't know it. So this is the setting. And how are we going to minimize our regret? So let's say that we need a couple of tools, so very basic tools. We're going to do linear regression, or regularized linear regression here. So at run t, the reward is this scalar xt, and we want to estimate the vector theta star that we don't know. So the vector theta star is going to be estimated by a Tikhonov regularized least square. And so, I mean, very standard definition, vt minus 1 times the sum of the actions weighted by the rewards. And at each run t, we define a confidence ellipsoid by this set of vectors in RD that are close enough to our estimator. Close enough in the meaning here that the distance in vt minus 1 norm, in vt norm, sorry, the distance is bounded by some sequence of scalars beta t that are here like a very important parameter of the algorithm that I will talk about later. But here, just assume that we have some way of constructing interesting confidence ellipsoids. Those are like a way to measure a distance in the parameter space around the estimator theta hat. And we're going to use them because we're going to try to be optimistic in this parameter space. So what does optimistic means? It means that we are going to try to choose the best action among all possible models in this ellipsoid that we defined. So more concretely, what it means is that the action AT that we are going to choose is the one among the actions that are available in our current action set, the one that maximizes a scalar theta for all theta in this confidence ellipsoid. So that looks a little bit like hard. In fact, the algorithm that was defined like that was called awful, but it's not really that hard. It's actually for each action A, the action set AT is a finite set of vectors. So for each action A, you can compute an index that is the maximum of the scalar product over theta belonging to a confidence ellipsoid. So you're maximizing a linear function on a convex set, an ellipsoid here, and this has a very nice explicit form. It's a very good exercise for your students in optimization. And you obtain this very nice explicit formula that is computationally efficient. And you're going to act, choosing each round, you're going to choose this one vector that maximizes this criterion ut of A. So maybe a picture is better than a sequence of equations. So here is the picture. At round t, I have an estimator, this is the red dot, a vector, an estimator hat theta hat of t, which is an estimator of theta. And I have a confidence ellipsoid. So here it's round because we have this Tikhonov regularization, so we have a lambda identity at the beginning. But you'll see, I'm going to show you a video of how it works. And at round t, for each of those green dots, which are my actions or arms in the Bandit vocabulary, for each of those actions, I'm going to compute an index and choose a vector that is here, the circled red dot, which is a A1. So it seems to be the best arm, because the best arm is the one that has the highest scalar product with theta. So this is going to be the best arm in that case. But I want to show you how it works. So it works like that. At the beginning, you have confidence ellipsoids that are round, and they're going to kind of take this ill-conditioned space, no, ill-conditioned shape, because you're pulling a lot this action in the direction of the action that gives you a lot of reward. But sometimes you see like UCB chooses an action that is like bad, and this kind of reduces the uncertainty on the ellipsoid in one direction, and you get a rounder shape. And this is how you regulate exploration versus exploitation. Exploitation is when you pull in the direction that makes your ellipsoid look like very extended in one direction, and exploration is when you reshape your ellipsoid of confidence. That's LinUCB, not any more complicated than that. So I go back here, yeah. And so now the question is, what is the regret of LinUCB? So we make a couple of assumptions that the rewards are bounded and that the parameters in the actions lie in a bounded subspace of RD, and that we have those nicely defined confidence ellipsoids. And we are going to show that the regret is bounded by square root of dn times the bn coefficient. This is going to be actually a very important term, times a log d plus n whatever term that doesn't cost us too much. And we're going to see how to prove that. It's actually not very complicated up to the fact that you need to know how to build those confidence intervals. But I mean, this is, I'm going to show you how it works. So first, the first step of bounding a regret is you have this sum of scatter products that I rewrite sum of RT, and using Jensen, you have square root of n sum of RT square. And now the game is to bound RT square. So you have, first you want to rewrite the regret, you want to rewrite the instantaneous regret RT in a more usable fashion. So the first step is to define this theta tilde vector, that is the one that realizes the maximum in this optimization problem that defines the action. So you have this theta tilde. And now, using the definition of UCB, I am going to bound A star being the optimal action, A star scalar theta star. So how I'm going to do that? The first step is to say A star scalar theta star is bounded by its UCB. That's by definition of the confidence interval. So with high probability is true. Then second step is to say, okay, but I chose AT, so it means that the UCB of AT was larger than the UCB of AT star. So I have the second step of the inequality. And then this UT of AT is just the scalar product with a theta tilde that realizes the maximum. And I plug this new expression of AT star scalar theta star in my expression of the regret, and I get a bound on the regret that I can bound by Cauchy-Schwarz, but not any Cauchy-Schwarz, a Cauchy-Schwarz with the VT norm. So I get the Cauchy-Schwarz inequality that gives me AT VT minus 1 times theta tilde minus theta. Theta star. And I bound this using the definition of the confidence ellipsoid. I get the square root of BT to replace the distance between the thetas, and then 2 times the VT times the VT minus 1 norm of AT is just due to me making a little mistake and forgetting an assumption on RT, but it's like, this is what it is. Actually, no, it's better than that. It's like 2BT is the actual diameter of this confidence ellipsoid. So here you go. You have a bound on the instantaneous regret. And now you have a new bound on the regret, which is 2 times the sum of the square root of beta n times the sum of norm square of your action. And this is like the last part of your proof. And it's like this, you need to call for this elliptical potential lemma that was proved in 2011 by Abbasi et al. And that gives you the last ingredient of your proof that bounds the sum of square. It's like a potential, it's like an additive term that costs you a little d log of something. And that's going to be the square root of d in your bound. So The last ingredient that you need to rewrite this regret expression, the last one, the right-hand side on the first line, is this beta n. So this is kind of the expert slide. It's just to show you what is the expression of beta n to give the final bound on the regret. So you construct the CTs using these beta t's that are that have this expression like in square root of log 1 delta plus log of something, and this is actually there's a d, I think, yeah, d log or something. Yeah. So anyway, so the beauty of those beta t is actually that they hold for any sequence of action that is random, so it's a random design, and that is sequentially chosen as a random process. So each action is a function of all the past. So you need to have a concentration inequality that holds for a martingale noise, like that holds for a randomized sequence of action. So this is the hard part of the proof, to actually design and prove a tight confidence interval and have the tight BTs that will be like kind of your learning rate, your exploration rate in this algorithm. So I'm not proving it, I'm just referring you to this very good book. It's called Bandit Algorithms. It's written by Szepesvari and Lattimore. You can find it on banditals.com. It's very good. In chapter 20, you have all the proof in details on how to prove this kind of confidence intervals. So this algorithm was historically introduced, this problem was introduced to the literature by Abe and Long, and then Peter Auer was the first to have the idea of designing confidence ellipsoid and use the optimistic principle for solving it. And I mean, confidence ellipsoids and concentration inequalities were refined time after time by authors like Abbasi, Adkari, et al. And you have alternative ways of solving linear bandits. You have Thompson sampling. You can do like some elimination of the actions and things like that. But yeah, I will leave you all the references in the end. So in a nutshell, you have a regret bound in square root of dm times bn, and this bn term is going to give you a d, an additional d, and so you end up with a big O of d square root of n, which is actually optimal with respect to lower bound that were proved in the literature. So the key ingredients for the proof are basically Jensen and Cauchy-Schwarz, a little bit of elliptical potential lemma, and some very elegant confidence intervals that are self-normalized. So now what do we do with this toolbox, with all these tools that literature gave us when we have delays? So I want to quickly remind the settings. So we have the learner interacts with an environment that doesn't send the answers immediately, but like let us wait for a while. But in the system at Amazon, it was not exactly what was happening. And like, I mean, in many systems, what happens is that if you have a delay at some point, your learner is going to stop waiting. It's going to just say, okay, after something like m time steps, I'm just throwing all the data to the trash. I cannot store everything for an infinite delay, especially because like when you present an action, most of the time you're expecting a click, but most of the time you are not going to get a click at all. Like, and then what do you do with all this data that you've been generating? You cannot wait forever. So the idea is to put a window of finite size m that is given by your system, and each action that you made is stored, and at some point it's just thrown away, and only the actions that were converted into clicks are sent to the agent. So how do you learn in such a setting? So the answer, like just to formalize a little bit, we have still the same setting, actions, reward that are here assumed to be Bernoulli because they are clicks, but this doesn't change anything to the problem. And if the reward is larger than dt, you just don't get any reward, or you get a 0, like your xt is a 0. And I have an additional parameter to my problem now. It's this parameter tor m, which is the probability of the delay to be smaller than m. So it's actually the amount of data that is actually sent back to the agent. 1 minus tau m% of your data is just thrown away to the trash. So I will have to learn with like just a fraction tau m of the data that I've been pulling. So now I still have my matrix, my covariance matrix VT, because that I know which action I've been making. And I have this slightly changed BT vector, which is now the sum of the actions, weighted by xt times an indicator that says that the delay was short enough for the action to be sent back to the agent. And this BT tilde is can be split into two parts. The old actions part, the ones that were made when I look at it at run t, I have all the actions that I made like a long time ago, and I have the actions that I made early enough so that we don't know yet if they are converted or not. And I have a new estimator, which is VT minus 1 times BT tilde. But this estimator is going to be biased. Like, I mean, they are all conditionally biased, but this one is particularly conditionally biased because the last set of observations that are still awaiting reward somewhere in the buffer are not all IIT, because the probability of the delay being smaller than t minus s is not the same as for all the actions. So we have a little problem here, like all actions are not biased the same way because of their delay. So this is gonna like hurt a little bit our estimator, and we're gonna see how to kind of cope with that. And you could tell me, you know, if your actions are delayed by at most m time steps, why don't you just wait for n time step each time you make an action, and you include this observation in your estimator only after m time steps, because then it's never going to change. Either you got a click, either you got no click, but in any case it will be a zero if you got no click or if it's too delayed. So you could do that. Like it would be your baseline. Your baseline is I make an action, I wait for m time steps, and I include these observations that are in the buffer somewhere if there is a click or not a click right a long time after. So that would be the one that I call theta disk for theta discard, that discards the last n time steps. So that would be kind of my baseline. And I'm going to compare the algorithm like this, my estimator theta b to the estimator of this baseline in the future. So what's going to happen is that my estimator is going to be to have like a finite bias due to the last window of m observation, plus something that really looks like a lot like LinUCB problem with a parameter that is scaled by tau m. So I'm going to be able to use all the tools of LinUCB for all the observations that are old enough, and for the ones that are in the middle, they are just not going to be too expensive to us. Like they're going to make us incur a bias that we're going to bound, but it's not that bad. So what happens is I need new confidence intervals that include this bias, and in my optimization problem is going to turn out into a new optimistic index for my actions. Now I don't maximize just the scalar product plus some beta t norm of A. I need to choose the action that has an additional term m times the norm of A in Vt minus 2 norm. And this term contains all the biases that come from this weird window with observations that are still awaiting rewards, but it's not going to cost us much because it's just a finite and vanishing bias. So it's just an easy modification of LinUCB that is not more computationally costly, and in terms of regret bound, it behaves just as LinUCB, except that I have an extra d log n term that is nothing compared to the dominant term that is in d square root of n. And the only thing that I have is a dependency in 1/tau m, which is the delay, the fact that I'm learning with only tau m of my data. So, I mean, yeah, it's not a big modification compared to LinUCB. And in practice, just to show how it works, I have run an experiment. So here I set a horizon of time that is of length 3,000 steps. And I set delays that are in expectation something like 100 time steps. So in a real world experiment, it would correspond to some, I don't know, campaign that lasts for 3 hours. And delays are something around 6 minutes. And now I'm going to see how my regret varies when I have the m parameter between 250 and 1,000. And I'm going to compare my algorithm, the one that includes all the observation, with the baseline that just discards all the last m observations. And indeed, this baseline at the beginning, it makes action, but it doesn't get any reward. And only after the first m time step, it starts getting the rewards that come from the first actions. So it has like an offset at the beginning, because it has to pull actions linearly. So that's very easy to see on the last curve, where m is equal to 1,000. For the first 1,000 steps, the regret of the blue curve. So it's regret, so the higher, the worst, the lower, the better. So, the first phase of 1,000 steps is linear, and then this blue algorithm starts to learn. While my algorithm already includes observations in the estimator, so starts learning earlier. It still has this, bias in the confidence interval, so it's exploring more, but actually not that much, so it's not big cost. And so you have a regret that is going to scale like square root of n, d square root of n asymptotically. But because you're winning at the beginning, somehow you're actually in the end having a regret that is lower than the one of the weighting baseline. So, and this gap is very important in an industrial application where, I mean, if you tell your principal engineer that you're going to have your algorithm waiting for 3 hours and then something's going to happen, like they're not going to be happy. So it's better to tell them to update all the time. So yeah, in conclusion, linear bandits are actually a very powerful model for a lot of problems, and it's also very well understood. So as I said, there is this new book that is coming out, the Bandit Algorithms, that gives a very nice and well presented overview of the existing algorithms and proofs and technical mathematics that you need to understand those methods. Those techniques of LinUCB have been extended to generalized linear models, as well as to kernel regression, and so we know a lot about how to run this kind of exploitation algorithms. Yet, when you have to include external constraints or externalities, noise that comes from something that is not exactly your feedback model, it's always a little bit complicated to include in the model, so it requires work, it's a bit challenging. And sometimes you have use cases that are just, that kind of violates the bandit assumption. So sometimes when you make an action, it's going to kind of modify the environment in which you're playing, and then following this environment change, you're going to take another action, and then you're going to get a reward that you can credit to the first action that you made in some sense. Like in a general reinforcement learning setting, you take actions, but you don't get the reward immediately. You improve. You walk in your little environment. You change position in the space, but then the rewards you get them later, like in a delayed way, but not exactly in the same case that I just described. And in that case, you kind of have to go out of the bandit assumption and open the Markov decision processes box. And then you have other algorithms like UCRL or KL-UCRL. but this is a little bit of a different world. But still, the tools that we have in LinUCB can be used and can bring answers to this kind of more complicated settings. So I will stop here, and I thank you for your attention. I can take questions.
Is there questions to the audience?
Very nice talk. I have a kind of technical question about the first part.
Mm-hmm.
So you showed some upper bounds, and basically my question is, are these upper bounds tight? Like, it's just an upper bound, so is it, when you compare empirically or in theory, is it tight? And in particular in the proof, so you detailed the proof and you started with some Jensen inequality.
Yeah.
And I was a bit surprised that you may lose a factor there, because if you do Jensen on values that go to 0, the RT, then it's not tight at all. I mean, you lose a square root n factor there. Maybe I'm wrong. But I guess you thought more than me on that, so what's your...
Yeah, so, I mean, the question of optimality is indeed very important. There are lower bounds. We can prove lower bounds on the regret of linear, you see in the linear setting, that are in d square root of n. So it means that the dependency that we expect is like in d, on the dimension is in d, and on the horizon is in n, in the square root of n. And we have those kind of lower bounds on like for independent set of actions, like on the hypercube or on the sphere. They are proved in this one book that I mentioned, and so we kind of, in the minimax sense, those upper bounds are optimal. Now, one question that you can ask is whether you are optimal in a fixed design setting. Like, I give you a fixed set of k actions, and I want to know whether you are your regret, like given this fixed set of k actions, if your regret is going to scale, if you can find a policy that is going to scale optimally in the long run. And this is a very different way of tackling the problem, and it's been done much more recently with a very different kind of techniques, where authors show a problem-dependent lower bound, asymptotic problem-dependent lower bound that depends on the parameters of the problem, and then show that there exists an algorithm that is going to reach this lower bound asymptotically. And with they still have some bugs it's not the bug in the analysis, but there is still some gap. So in this one problem-dependent setting, the problem is not completely solved. In the linear setting like that, we have the minimax like optimality. So yeah, we don't have that though for Thompson sampling. Like, there's still a gap for the Thompson sampling analysis.
Yes.
I have a more general question. So there are a lot of reinforcement methods that you see in literature that use policy learning, but also Q learning. And often the Q learning is then used for introducing deep approaches or deep learning approaches. Mm-hmm. And I guess it's a bit, so my question is how is it related to the bandits in this case? Because those methods will be inherently be nonlinear. And the delay might be in the recurrent network that you can put in the Q learning, but I don't see, although the framework is very similar, I don't see a clear connection to your talk. Can you give a small hint on this?
Yes, so I'm not a big expert of all the techniques that people have in Q learning, but what I know is that in Q learning, usually you have a function approximation. You approximate this Q function by something. So one simple thing you can do is approximate it by a linear function. And then you try to estimate this linear function. And there are those algorithms like UCRL that use confidence interval on these estimates. Thing is, I don't know exactly it works exactly as LinUCB in the like all the confidence interval and everything. And I know that actually a lot of people, and it's this in the Sutton and Bartow book, they encourage people to use epsilon greedy as an exploration strategy. So you estimate this linear function, and then you fix your epsilon, and you only explore with probability epsilon. Now, I mean, if you could derive confidence interval like here, like in the linear function approximation, it would make sense. But sometimes this function approximation is a deep neural network. And then, like, there's no chance you have those confidence ellipsoids and those things that behave nicely. And then you have to, in some sense, do some epsilon greedy exploration. So whether this type of work exactly applies to a more general setting in MDPs, I know there are some works on that. I'm not a big expert, and I don't know how optimal you can find things, but yeah.
Thank you. The last question? No? Okay. Well, thank you again.